Next, we will talk about how we perform some operations for vectors. Because if you have vectors flying around, that's kind of pointless. If you just have a single vector just to describe a single transformation or a single movement, we need to find a way somehow to combine them and make sure that those combinations are making sense. They do what we need them to do, and they are useful. So first of all, before we dive into let me list all the operations. We can add, we can subtract, just like numbers, and we can multiply. But the interesting thing about this is there are actually 3 ways to multiply a vector, because it's not as straightforward as numbers. Like if you have 2 numbers, you can think of multiplication as a sequence of additions. You can think of 3 plus 5 as add 3 to 5 3 times. Sorry, you add 3 5 times, or 5 3 times, depending on what how you define the order. And so the nice thing about it is they are symmetric. You can perform those in any order, and that's how you multiply the numbers. But then when you multiply vectors, like it's not clear what you mean by multiplication. Like if you have 2 vectors and you multiply them, and what would the result be? Are you talking about the area of this shape that comes from these 2 vectors? Are you, I don't know, add them together in this way? We just keep adding them just to make a similar behavior as you add numbers together. They are in other ways. But we define multiplication in 3 ways. And these 3 ways will give you 3 different information. It's not like we multiply them in 3 ways and get 3 same results. No, we get 3 different results, like 3 different interpretations. And just an outline. You can have the scalar multiplication. This is to mimic the multiplication for the numbers. You multiply a number, any number, to a vector, and that will give you this similar way to interpret the multiplication as an addition. And so that's the basic, that's the default way you would think about multiplication. Second, we have the dot product. And this multiplication doesn't give you this kind of result. It gives you something totally different. And this happens to describe that there are lots of applications of the dot product, and that just seems to be like the nice way of combining 2 numbers or 2 vectors to get a new number. It can give you the information about the angle between vectors. Because again, when you think about them as lines or as arrows, if you have 2 vectors, 2 arrows, then there is an angle between them. It's clear there's an angle between them, and that should be a nice way to find that angle. Then you can talk about the projection. This is also another important aspect of computer graphics. If you have an object, that's a classic question. You have an object, you have a light source, and you need to make a shadow. The question is how to make a shadow. Is there a nice formula to transform from the vector, like for this object, and to give it a shadow? It's about projection. And there are lots of other things that happen to have a dot product as a formula. The thing is, the other things they are not obvious that they are related to angle directly. And sometimes you want to find some quantity. You go to Google, find some information, and they give you a formula with a dot product. And then you ask, wait, why is dot product there? And what's the point of taking a dot product? Maybe because sometimes you just want to add this to multiply these two numbers together. But most of the time, the two basic things, like whenever you treat a dot product, that should be related to either the angle or the projection of that vector. And lastly, we have the cross product, which we don't use this in this class. You can find examples online, like whenever you have to encounter that kind of vector. But just to give you an idea of how many ways we can multiply the vector. Like cross product happens to have a nice interpretation in 3 dimensions. You have to make it like 3 dimension only. But you have 2 vectors or 2. You can think of it as like 2 sticks put together, and then there's like a nice vector or a nice way you can put another line, the third line that make the right angle between this new vector and two other vectors. You can think these 2 vectors, original vectors, as like I don't know, a pole or a lines or a wires, and you need to make a pole like upright on the ground to connect these 2 lines together. And so that's one. That's another way you can multiply them. But again, we don't need it, because to know the cross product, you need to know the matrix determinant or something. So we have these 2 products. It's a way to multiply vectors and scalars together. And so if we have that, just the multiplication. And you might ask, do we have division? And the answer is no, of course. Sometimes you can divide vectors by some numbers to scale it up and down. But you cannot divide one vector to another. But also because we don't have this kind of question. Because this question doesn't come up, so we don't need to define that. And second of all, there's kind of but usually whenever you encounter a new topic, you want to divide something, right? Almost always you can replace it by this kind of multiplication instead. And so to divide by 2 is the same as to multiply by 0.5. You can translate, you can change the language of division into language of multiplication. And once you translate that into this new language, then you don't have to worry about, divided by 0 or other stuff. You can use the same properties, the same principle, the same definition of multiplication. We have just one operation to worry about. So we don't have division for vectors. Cross it out. And finally, the last operation we need is the norm. The fancy word is the norm, which maybe I should not use it at all. But what it does is it computes the size of the vector. Given a vector, you can find the size, or you can find the magnitude from the initial point to the terminal point. And so these are all we need. Addition, subtraction, scalar multiplication. It is a scalar multiplication. That's a dot product, and the size of the norm. And we again for this class, for the introduction class, we only need these 5 operations. That's enough for us to describe a basic of transformations of vectors or of shapes or of anything that you can draw on a plane. Those are the 5 you will learn in this class. And let's see what they are and how do you find them. Oh yeah, I also have this in the next one. And also the dot product. Yeah, I should also add that. We can take dot product and we can find norm. Oh, and some extra interesting fun fact or definition. The x is a 0 vector. And just like you have 0 in the number. For the vector, the 0 vector is a vector that does nothing. It means the initial point and the terminal point are the same point. You can think of it as like the lazy one. It does nothing. Which instead of using just a number 0, you need to add an arrow on top. We talk about a vector 0, not a number 0. And the basic property is that since it does nothing, when you add that to another vector, you still get the same vector out. You don't add anything to it. And you can multiply a 0 to a vector to make it to turn a vector into a 0 vector. Which we'll see in a moment. But first, we will see the basic operations. Oh, I switched it to slides. Okay, so first we have addition and scalar multiplication. If you just need a computational formula, these are the formulas. Okay, but if you ask why do we have to define them in this way? And I think the clip did the clip that we watched at the beginning has some nice kind of good question. And you should let's say you have a vector u there. Do you have a vector v there? So u represents like a movement to the upper right corner. V represents a movement to the lower right corner. And what if you want to add two vectors? And there are two questions. Right? So first is how. The first question is why. Okay, why do we have to add vectors? And then once you know why, you have to ask how. So that if you just draw this image, maybe I don't know, maybe you attempt to just connect them together and to make a line. Define this as an addition. Maybe you can, of course, but it doesn't make sense if you think about a vector as a force or as a movement. Because if you think about if you have an object, if you think about u and v as a force or movement that push the subject to a new position, and if you think this orange as like your finger, you push an object and it moves there, and that's a new position. So you apply that vector. If you reset to the origin position and you push it using the other vector v, then it moves to this position. And if you ask about you adding force, two forces together to push an object, so yeah, you push your fingers on the same object and then push them all together. And you won't expect it to move this way, right? You won't expect it to move this way. And that would be weird, isn't it? Or neither this one. It's not natural to move up or down in this way. This would happen if you just connect the endpoints together. And so this doesn't make sense. And what do you expect to see after the movement is you should when you combine force, and this should move kind of like here. You think about you can try it, of course. Maybe it's difficult to see in this way, but let's say you move right and up. If you exert the force on both of your fingers to the object, now this object should move like here. If we natural, it moves here. And so that's why we define addition in this way, because we want the addition to be the combined force or the combined movement. And so the way we apply the addition is we move. Let's say we copy that, not the whole thing. Okay, there it is. We copy and paste. Oh no. Where are we now? Okay, there. And paste. Okay, and then yeah, and then move there. And then here we have the combined movement of these two forces. And so we naturally, like, the object should move this way. And also the way you combine is interestingly, when you move object, like when you apply two forces to the same object, it is the same as though you move one object. You apply the first force first. Yeah, so this green object will move to this orange position, and then you apply the other force, like the other vector. So it moves there. And so that's how we define the addition. That makes sense in the terms of what we needed to do for us. So this is the result of adding two vectors together. So to give a discrete example, so let's suppose you apply vector 3, or that should be 1 and 3. 1 and 3. So let's say that's a vector v. There's a pink one, and then you apply the vector u. Let's say that's a 2, 2. So we see what's going on here. And so we add these two vectors together. So what you do is you copy that. Yes. Move it there. So you move the initial point of the second vector to the terminal point of the first vector. So you push the object there, and then you push the object there. And the combined force is the same as if you just put it all the way from the origin to the terminal point of the second vector. So that's this v plus u, or v plus u. And how do you compute that? You can see from this image. If you let me remove that because it's getting clogged. So if you imagine, if you just look at the x coordinate, you move one step here. So this has length 1 from the vector v, and then this vector u tells you to move 2 steps to the right. So that's 2 steps to the right. And so if you move 1 step to the right and then 2 more steps to the right, and that's the same as moving 3 steps to the right. So that's 2 plus 1 visually. And of course, that's the same thing as the other direction. If you move 3 steps up, using the vector v, using the first movement, it's 3. And then you move 2 steps up, using the vector u, the second one, you get 3 plus 2. That's how you get 3 and 5 as the final vector, as the final addition of these vectors. So that's how you define the vector addition. And so that's that. If you have negative numbers, if let's say v is up here and u is down here, then of course you just still add the same numbers together. You can add the first number as the first components, because that tells you how many steps you walk in the x direction. And so you move v there and then w there. And so the x is still the sum. And the y coordinate, actually let me give you again. For example, so let's 1, 3. Let's say that's 2 minus 1, 2 minus 2. And so the result of these two vectors combined. Let me zoom in. You combine them, you get this addition. And that's the result of u plus v. So you walk 1 step into the right and then 2 steps to the right. So that's 1 plus 2. And then for the y coordinate, you walk 3 steps up because it's a plus, and then minus 2. So you walk 2 steps down. And when you add this all together, you get 3 and 1. That's the result. That's the purple vector. If you combine these two vectors together in this way. Right, so that's the addition when you combine force to get a new force, to get a new vector. Then we also have subtraction. Yeah, but before we go to subtraction, we need to come back a little bit and see what it means for the scalar multiplication. What it means for us to multiply them using a scalar. So if you have an object, you can see on the screen like that. That's a vector. That's an object. If you copy that using any software you have, you can see we can do what? Scale. And scale up or scale down to make it tinier. And again, that's an intuitive way to apply it to change the vector. And it doesn't work here. But I think if you use Photoshop or if you use any image editing software, it also allows you to scale it back. It allows you to scale it back to the other direction. And that's how this works. It should work now. Yeah, we scale back. Okay, so scalar multiplication is a way of extending, or scaling up, or shrinking the vector, or changing the direction. This have like 3 combinations combined. You can scale up, you can shrink, or you can reverse or flip the vector to the other direction. And these are it's all the same thing. We perform these operations by just multiply that by a single number k. It's just how we think of the number k. If k is greater than 1, you think about it as a scaling. You scale it by the factor of 2. That means you increase the size by 2, or 3, or 4, or 5, or 1.5. That's the effect of scaling. If you shrink, it means you use the scale. The other factor is between 0 and 1. You shrink it to 0.5 or half of its size, or 0.3 or 0.1, depending on the number. Or you can reverse it. You reverse means you flip direction. This means you multiply by k to be a negative number. K is less than 0. And this is also going to be handy when you want to to rotate 180 degrees. It's the same as to flip or to reverse it to the other direction. And so this has some slight connection to the rotation. And so that's the multiplication. But the way you compute it, you simply distribute the number inside the vector. And so for instance, if you have the vector v up here, let's say that's 2, 1. Okay, so it's 2 steps to the right and 1 steps up. If you want to scale it up by 2, well, let me prove it a little bit why it works this way. You scale it by 2. First, you think about it as you add 2 vectors together. You add the same vectors together. This is what you would end up with. And so this agree with the definition of multiplication. If you have 3 times 5, you have 5 copies of 3. Actually, in this one, we use 3 copies of 5. So if you multiply a number to something, it's the same as you adding the same thing repeatedly. And how do we add two vectors together? Like we saw it above, right? If you have, let's say this is AB, this is AB. Just add these two together. That gives you what? A plus A and B plus B. And that's how we finally distribute it inside the vector notation. So scalar or scaling, that by a factor of a number. Oh yeah, by the way, this is called a scalar. Is it a real number? But we call it scalar because we want to make a distinction between the number in the front here and the vector on the back. So we need to give it like a different fancy name. Okay, so here if you have a vector 2, 1, if you scale it up by 2, you get of course 4 and 2. That we compute it by multiply a number into the vector notation. The way you write is if you write as variables, you just stick those two notations together. But if you translate that, if you change that into a number, you can write it this way. It's just a number, and then just write the vector notation. And then when you distribute, I just distribute as though you distribute that into a parentheses. That 2 times 2, and then 2 times 1. That gives you 4 and 2. So that's the result. And then we can see here from the formula. So if you multiply by a positive number, then that's intuitive. Like that's fine. Let's see what happens when you multiply a number by a negative number. Let's say if you multiply v by -1. If we define in this way, let's say v is the same vector 2 and 1. 2 this one. Oh, ignore this top half for a moment. Again, I flip it. If you just multiply it from the definition we have there, right, so what you do is you distribute this number -1 inside. You have -1 times 2 for the first component, and comma, and then -1 times 1 for the second component. So you have what we have, -2 and -1. And then if you go back to the graph and write this vector, the -2, so it's 2 steps back and 1 step down. So that's the result. Here's -v, -1 times v, which of course we can abbreviate it, as you can see up here. That's just -v. So that's what I mean by multiplying a number by a negative number, by a negative one. Flip it and see it here. And what if you multiply it by -2 or 3 or something? And here you can think of it as you can think of the number -2 as -1 times 2. Let's expand it, split it into 2. So this is now we see the first step of understanding this as a sequence of operations. Like when you multiply by -2, right, you can think of it as first you multiply it by 2. So let's say here, let's say we have a vector v here. That's v. First we multiply it by 2, so we get the larger version, the 2 times s large. That's a new vector, 2 times v. And then you multiply -1 to that vector. If you multiply -1 to a vector, it means you flip this vector to the other side. So this is negative of 2 times v. And so you can think of it now as you have applied 2 operations or 2 transformations, one at a time. You scale it up and then you flip it. And also, that's the result. And also, you can think of it as 2 times minus 1, because you can switch place of for the multiplication. Right there. What is it called? Associative? Not that. Symmetric. So also this can be thought of as you flip the vector first. Right, from B you get minus V first, and then you apply the multiplication. You scale it up in the flipped direction. So if you flip it here to this, then once you scale it up, you get the same vector. It's 2 times minus V. So that's how you interpret multiplication by a negative number that is not minus 1. Alright, so that's the second operation. Now we have a third one. And interestingly, I put this as third one because it's subtraction. Now I think let's say I don't like the way Thai school teach vector subtraction. So I will tell how they teach you at the end and use the way I use. And so if usually subtraction is not well defined. Like, you have to wrap your head around. Like, you know 2 plus 3 is 5, right? Hopefully. And if I then ask you what is 5 minus 3, it's 2, of course. But like how do you explain this kind of operation? If you think about a number, you start from 5 apples, you eat 3, and then you ask how much you have left. And so you have kind of like 2 different operations together. But another way of thinking about subtraction is this number is the reverse function. So you think about something that when you add 3 to that, you get 5. And so this question of asking 5 minus 3 is asking if I have 3, how much do I have to add to get to 5? How much do I have to add to 3 to get to 5? Oh, yeah, that's the difference between 5 and 3. But this is actually how the subtraction is defined. And maybe this example is too simple to think about. But it is useful when you start learning some other operations like multiplication. Like 2 times 3 is 6. If I ask 6 divided by 2. And then again, it's about asking to multiply by what? Get to 6. And this gives you the intuition about, okay, you divide things in groups of 2. And you ask how many groups are there. And then if you remember, this is when we go one step higher, when we talk about exponential, 2 to the third is 3. That's the same as asking, what is log with 2 of 8? And again, this is the reverse function. And people have hard time understanding the logarithm function. And so what I just suggest is you go back and to the first definition and ask, okay, 2 to the what is 8? This is asking for the number that I can plug in here to make this true, to make these 2 sides of the equation equals. And you can see, oh, it's 3. You have to raise 2 3 times to get 8. So that's how you think about the inverse function. Oh, why do you have to say all this? Because similarly, when you think about vector addition, you have this image in mind. You have U, you have V, and you have this result. But if I ask you about the vector subtraction, what do you mean by subtract? It can be Can we do better? Can we change that to something that we know? Oh, it's getting dark. And the thing is, just like of these examples, the first step is actually to like convert that back to the question about addition. And so instead of subtraction, you can think about it as the addition of the negative number. And just like we do with the number. Like 5 plus 3 is the same as, think about it as 5 plus minus 3. So we have one number, we have another number, we can add those two numbers together to produce a new number. And it's the same thing here. When you subtract vectors, and there are two ways. I will show you another way too. And you can think about it as this. And I think this is the easiest way. I don't know if this is the most preferred way for me. So for instance, if I have this, if you have the same vector u and v there, u is up, v is there, then minus v is the flipped version, like it's the reverse version. That's the minus v. So you can think of u plus minus v like as adding these two vectors together. And so it's easy to see that it is u here. You add, like you apply another force or another movement, which is minus v to this direction. So the result is the same as you start from the start and go straight there. And so that's u plus minus v. So you can subtract. By definition, the subtraction is the same as you add the reverse version of the second vector of the one with the negative sign. And so that's how you think about subtraction. Another way to think about subtraction is, I think this is close to what you are taught in school. Is okay if this happens, it is equals to something w. This is what we want to know. That means that you can use the usual trick about the addition where you can move things around. I should make it w. Then u is the same as w plus v. This is what I mean by the reverse function. To find the difference, that's the difference. It's the same as if you add the difference like to the vector with the negative number, you get the left one, the one with no sign in front. And so the difference between the two here, it means that we can like add this back to the v to get back to u. Just like if you have like 5 apples, you take 3 offs, you have these 2 left. And so this is the quantity that you can add back to get to the vector u. And so if you think about this, in this addition. And so what you have here is we have vector v. Okay, that's we have vector u and v. That's u. That's v. And so the question is, you want to add v to something to get to u. And so you start from v, you have to add something to get to u, and that's something. And you can see here is this thing. And this w, this vector is a vector that when you add to v, you get w. And so this is again, this is what you are taught in most Thai textbook. You have to subtract, like you lay it in this formation and connect the terminal point to terminal point. Which is again difficult to see. But if you erase that, like it should be clear that you add these two vectors together to get this result, to get u. And so this must be the difference. This must be the result of subtraction. So that's how you subtract visually. And of course, if you just want the numbers, you subtract by just subtract it component wise. You subtract the first component to the second component, so it's 3 minus 2. And then you subtract the first component. Sorry, the second component to the second component in the order. And the result is 1n minus 1. It's kind of disappointing and it's kind of clueless if you just do it numerically. But I think more important and more interesting is how you actually think of them in terms of movements. So these are the two basic operations of addition, subtraction, and scalar multiplication. At first, I suggest you draw some graphs to give you an idea of what the result looks like. But eventually, when you have to code, or when you study this in a higher level, everything will just becomes a number. Okay, so that's the three operations we have and what they mean. And we have some basic properties. You don't have to memorize it. But if you understand what vectors are, how you subtract, how you add, how you multiply by a scalar, then this, let's say 4, 5, something, comes out naturally. For instance, let's make it 2. If you multiply the product by 2, what it means? Let's say you have u here, you have v there. The addition. If you add them up, you get this u plus v. If you then multiply the result by 2, that means you scale this up by 2. So that's the 2 times u plus v. If you add first and then multiply. But if you think about it as visually as an image, you can see that this can be constructed if you also add this curved triangle. It's as if you scale this triangle up 2 times. And if you scale this triangle up, you would scale this vector u originally into this new vector, which is 2 times u. This longer vector is 2 times u. And also this longer vector in the other direction is 2 times v. And so we can see that this green vector is this pink plus this orange vector. And that's what we have here. And that's the result of what we call the distribution. Distributive property. Which makes sense. We have 2 copies of the multiplication. And second is kind of makes sense. Because this works the same as as numbers. If you have v, you multiply by a, you get a times v. Multiply by v, you get v times v. And then if you add them together, that's the same as you just multiply by a plus b. That's what the second means. Third and fourth one are kind of just a note. When you multiply a vector by 1, it's the same. You don't scale anything at all. And that's why you rarely or you never see a number 1 in front of a vector. Because that's the same as the vector itself. And also when you scale when you do the math, at the very end, when you simplify numbers, you would remove this one. The first one is what we already described. Actually, this is the key of the minus. You can get rid of minus everywhere. You think of it as a vector multiplied by a number, multiplied by a scalar. That scalar just happens to be a negative number. And lastly, we have an interesting. It is both an observation and definition. And so if v equals to a times w, we have 2 vectors, and we can relate these 2 vectors by multiplying a scalar to a vector. to get the other vector. Then we say that these two vectors are parallel. This makes sense, right? If you think back about, okay, if you start from V, and then you scale it up by any factor, then they still point into the same direction. Because we scale both the horizontal and vertical aspects. But then sometimes it's not at the same origin. Sometimes they don't have the same initial point. And sometimes you are asked to compare this point, let's say 0, 1, 0, 2, 2, and another point, let's say R, which happens to be, let's say 2, 3, and then the point S, which is, let's say 6 and 5. Now it's not clear anymore whether this vector and that vector are parallel. That will be the question you want to ask. And so the way this works is to check whether these two vectors are parallel together to each other. You find the vector first, and then you want to find. You try to find if there is a constant A where you can have this equation. Is there a constant that makes this vector V in the bottom and vector U on top to be the same? And in practice, the way we do is we first write the vectors out. So we have V here in the bottom. V is we walk how many steps? 2 steps. And so it's 2 minus 0 for the first component. And then how many steps up? 2 minus 1. So it's 2 and 1. And then we have another vector U. If you compute the x component is 6 minus 2, which is 4. The y component is 5 minus 3, which is 2. And so to check whether they are parallel, you do not have to measure angles or anything. You just have to find a number A or any number such as this equation holds. Did you have some do some math? Right, but here it is clear that that number is 2. Actually, if you want to write an equation for that, and then sure. So that means if you expand this out, we want to make that 2, 1 to be the same as some number that we want to find, times. Sorry, it's not 2, it's 1/2. Equals to that. And then for two vectors to be the same, first we distribute A inside, so we have 4 times A times 4, or we switch it to be 4 times A, and A times 2, which we can swap it to 2 times A. And then we solve 2 equations. Does this sound familiar? We have 2 different equations, and we solve for the number. So we want 4 times A to be the same as the first component, which is 2. And we want 2 times A to be the same as the second component, which is 1. And thus these two equations happen to give you the same solution, which is A equals to 1/2. So that means the answer is yes, we can find such A. That's the way to scale one vector to match or to overlap with the second vector. And so that's a fact. Is it useful in calculus? And actually, if you want to study how shape works in a higher level, this fact is also used very broadly. But just for now, just to mention this fact. Okay, so these are all the basic operations. Oh, this one it's not basic. It's gonna be the next part. Oh, yeah, maybe do some exercise, take some break, and we will see you in the next part.